Okay, so I'm Nicole from Seychelles School, and my presentation is on a novel approach for Twitter hate speech analysis and detection using deep learning models in web scraping. So online instances of hate speech are extremely common on virtually all social media platforms, and 53% of Americans have said they were targeted by hateful speech online, and 37% reported severe attacks. But sites like Twitter still rely on an artificial intelligence algorithm that is only around 50% effective. This algorithm often misses instances of hate speech. Even though deep learning methods for hate speech detection are able to outperform state-of-the-model car or word n-gram methods by nearly 18 F1 points, there still remains a lack of accurate enough deep learning models that can both detect instances of hate speech and categorize them. One of the most successful binary hate speech classification models reached an F1 score of 84.83% and an AUC score of 90.39%. The most successful multi-class toxic sentiment classification attempt only reached an AUC score of 82%. Additionally, only around 50% of tweets violating Twitter guidelines are flagged by AI, while the other 50% have to be manually reported by other users. The methods behind these models, such as the CNN LSTMs and the use of F1 and AUC scores, served as metrics for this project. Furthermore, very little research has been done on the relationship between hate crimes, hate speech, and geographical locations of incidents, which served as motivation for the chloropleth map component of this project. And TweetWatch is a platform that automatically reports tweets marked as hate speech by passing real-time Twitter data through two novel deep learning models, a binary convolutional neural network, a CNN, to detect hate speech, as well as a multi-class CNN to classify hate speech into 5 categories: sexual orientation, special needs, gender, race, and other. Moreover, the solution includes an accessible interactive chloropleth map of the United States created from the collected data. Previously, little effort has been made to find a correlation between geographical location and hate speech frequency, which TweetWatch solves by using its innovative chloropleth map. Furthermore, the deep learning models created for TweetWatch are significantly more accurate in terms of AUC and F1 scores. To prove results, AUC and F1 scores were used to evaluate the accuracy of both models and select the best combination of batch size and epochs. Finally, we evaluated the reliability of the binary CNN through AUC and F1 scores, which were evaluated for 9 combinations of different batch sizes and epochs. Secondly, we similarly evaluated the reliability of the multi-class network using AUC scores, also for the 9 combinations of different batch sizes and epochs. Our objective for the 2 deep learning models was that the AUC and F1 scores of the novel binary classification model and the multi-class classification model must show over a 5% increase from previous state-of-the-art models. So now a deeper dive into what TweetWatch is. TweetWatch, our system consisting of multiple components, is a multi-step hate speech detection and categorization algorithm that automatically reports tweets marked as hate speech by passing real-time Twitter data through 2 novel deep learning methods: a binary convolutional neural network to detect hate speech, as well as a multi-class CNN to classify hate speech into 5 categories. Natural language processing, such as tokenization and vectorization process, is used to optimize the accuracy and efficiency of the neural networks. Through the use of dual neural networks, TweetWatch is able to go beyond simple identification of hate speech and also provide instant analysis of the frequencies of hate speech in different locations and categories. Live Twitter data is scraped using the Twitter API, and tweets flagged as hate speech by the binary network are passed to Google Firebase. Then the multi-class network pulls data points from Google Firebase and categorizes the data, allowing TweetWatch to integrate the collected data into a publicly available interactive chloropleth map of the United States. TweetWatch utilizes the TweetPy library and the Twitter API to scrape real-time tweets, as well as information about the users, such as the location of the users. The scraper also standardizes the data, such as by removing leaks and reconfiguring emojis, to ensure that the format of the real-time data reflects that of the training data used for the convolutional neural networks. The collected data is passed to Google Firebase, where the data points are then sorted by properties such as location. New data from the web scraping algorithm is passed to the Firebase every 2 minutes. And to create the binary convolutional neural network, a total of 40,000 tweets were used to train the model. The data was debiased by making sure there are counterexamples of data that contain hate speech keywords, and standardized by converting to lowercase and removing links, usernames, and non-ASCII characters using regular expression operations. Then standard NLP data preprocessing was utilized by fitting a Keras tokenizer on collected tweets to split strings into tokens and using spaCy to create text embeddings. The final model compiles the model with the Atom optimizer and binary cross-entropy loss function and uses layers such as conv1d, pooling, dropout, and dense. To train the multi-class convolutional neural network, more annotated datasets of Twitter hate speech were collected and debiased. The datasets were then manipulated to fit into one or more of the predetermined labels. The NLP-aug library synonym augmentation function was used to individually augment each data frame to reach 12,000 tweets for each label, and a convolutional neural network was constructed using the leaky ReLU activation function and the convolutional layers such as pooling and spatial dropout. The model was compiled with the Atom optimizer and categorical cross-entropy loss function. To evaluate the reliability of the binary convolutional neural network, 2 accuracy metrics, AUC and F1 scores, were evaluated for 9 combinations of different batch sizes and epochs. A grid search was utilized to optimize the efficiency of the evaluation, and the obtained metrics of each epoch were recorded to construct training and validation curves. After grid searching, the most accurate binary classification model had an AUC score of 98.95%, an F1 score of 97.88%, and consisted of a batch size of 512 and 22 epochs. The reasoning behind the higher accuracy for 22 epochs when compared to 50 epochs is likely because the model overfitted between 22 and 50 epochs. The training and validation AUC and F1 curves for the best performing binary model show a dramatic increase per epoch until it converges. Similar to the experiment for the binary CNN, 9 combinations of batch sizes and epochs were used to test the accuracy of the multi-class CNN with different parameters. Once again, a grid search of these combinations was used to analyze the accuracy of the models with respect to its AUC score, and the training and validation AUCs were recorded at each epoch to track the improvement of the model through the course of its training. After grid searching, the most accurate multi-class model had an AUC score of 89.46% and consisted of a batch size of 128 and 50 epochs. The training and validation AUC curves for the best performing multi-class model show a steady increase per epoch. Furthermore, using Dash by Plotly, data is collected from Google Firebase every 2 minutes and reconfigured into an interactive choropleth map of the United States. The choropleth map uses a logarithmic scale to measure the frequency of online hate speech in each state. By hovering over a state on the choropleth map, users are able to view the corresponding breakdown of categories of hate speech in each state. The final metrics for the binary classification model were 98.95% in terms of AUC score and 97.88% in terms of F1 score. These metrics surpassed the performance of models from multiple papers, including a 9.47% increase from the AUC of 84.83% and a 15.38% increase from the F1 score of 90.39% set as the baseline. The final metric for the multi-classification model was 89.46% in terms of AUC score, showing a 9.10% increase from the performance of the baseline model, which had an AUC score of 82%. Furthermore, all metrics greatly surpassed the 5% target set in the objective. Random variables such as the order of the data passed into the model and layer outputs dropped through the dropout layers could have influenced the results both positively and negatively. However, repeated trials with small standard deviations show that the randomness did not drastically affect the results. The third part of this solution, the chloropath map, is able to accurately provide real-time geographical analysis of hate speech. It updates once every 2 minutes, making it the most recent and relevant chloropath map for hate speech in the United States. In conclusion, despite an increasing amount of hate speech on Twitter, there remains a lack of comprehensive deep learning models that can both detect and categorize hate speech. In this project, TweetWatch was created to serve as a comprehensive detection and reporting platform. TweetWatch utilizes two CNNs, a binary classification CNN to detect hate speech from real-time Twitter data, and a multi-class CNN to categorize hate speech into 5 categories. We used Dash by Plotly to create a real-time chloropath map of the United States with respect to frequency of Twitter hate speech in each American state. By using the AUC and F1 scores as metrics, we showed that the novel deep learning networks are more reliable than previous models in multiple papers. The binary classification model had an AUC score of 98.95% and an F1 score of 97.88%. The multi-class classification model returned an AUC score of 89.46%. The chloropath map provides real-time geographical analysis of hate speech, which supports the proposed solution because it is able to accurately provide real-time geographical analysis of hate speech, which fills the gap of the lack of data on the relationship between hate speech and geographical location. Thank you.